Let's do this. Draw a tackle to lift the load by applying the force in downward direction. So the figure given is this. So this is the figure, like three pulleys are in the upper block, which are fixed. They are fixed. And here there are two pulleys in the lower block. And here is the load attached. So this figure is given in this question. And we have to put a tackle on this such that we are applying force downwards. The effort direction will be downwards. Let's go ahead. Mark in the diagram direction of load and effort. B. If the load is raised by 1 meter, through what distance will the effort move? C. State the number of strands of tackle supporting the load. D. What is the mechanical advantage of the system? So let's first do first thing, which is putting a tackle. So here I have shown in diagram step by step how we can go about this. So let me put that properly. So load is down here a little bit. So what we are going to do, because we need effort downward, so we will start from here. So we'll start putting the tackle from here. Okay, then we'll go block by block. So we will cover this upper block's first pulley, and then we'll go downwards, and then we have joined now to the other block, right? So block by block we need to move. We'll not go like this, right? Within the block we will not go. Okay, so let's go back to the first block, upper block. Now this pulley we will cover and we'll go to the lower block. We'll wrap this. Again, we will come here. And now lastly, because now there is no pulley to go to, we will wind it here. So this is the step by step I have given in 4 steps how we can do. But this is the way we need to put. Remember, whenever we are putting the tackle, we also need to tell what is the direction of effort. So we are pulling downwards because that was given in the question. And effort will be, load will be downwards. This side, this will be load. And also we need to mention what will be the tension. So due to this effort, because we are using one single rope, so this effort is only the result of the tension in the rope. So this will be everywhere. Okay, everywhere the tension is same. So here if I ask what is the tension above, it will be equal to E. And if we denote by T, so T will be upwards. Second, so I'm counting now number of strands: 3, 4, and 5. So there are 5 strands. If we look only to this area, you'll be able to see 5 strings which are supporting the load which is going downwards, and these tensions are pulling them upwards. So let's go ahead. As there are 5 strands supporting the load, VR, velocity ratio, is equal to 5. So number of strands will be equal to how many, how much the velocity ratio is. So that is one thing we need to see after drawing the tackle, how many strands load is getting supported by. So that number itself is a velocity ratio. Now we can see distance moved by effort. This is a definition of VR. VR, if you take this side, so distance moved by load and distance moved by effort, that ratio is called VR. So I'm just taking this side because we want distance moved by load is given to us. So we'll put 1 meter here. Distance moved by effort we don't know. So we will put 1 by 5 and we will get 5 meter. So in this diagram, right, if this load moves up by 1 meter, 5 times this effort will go down. Okay, so nothing is free. So if we have to apply, it is not like here the load is coming by 1 meter up and here also only 1 meter distance we need to cover. We have to cover more distance because we are compensating for the force. So displacement should be more. So the effort will go down 5 times the load coming up. That is what the velocity ratio also gives us the intuition. Okay. Now what about mechanical advantage? They have asked for mechanical advantage, but strictly speaking, right, without knowing actual load and force, mechanical advantage cannot be calculated. So this we should put a note, because they should have told like how much force is required. Then only we can take, mechanical advantage. But if it is not told, we will tell clearly that we are assuming then. We will assume that system is ideal. It means the block and tackle system which we are using is ideal, 100% efficient. And in that case, mechanical advantage will be equal to VR, right? Because efficiency is MA by VR. VR we know, right? MA has to be equal to 5 because we need to get efficiency of 1 for ideal machine. So this is one, special mention to this question. So because in the question they have not told where the how much load is there, how much effort, that information is not given. So we have to assume and note them down very carefully, not just going blindly and saying like no, MA will be 5. So we should be having a good reason behind it. Let's go next. So assuming the ideal system, MA will be same as VR, that will be equal to 5. So number of strands of tackle supporting the system is equal to VR. However, the same conclusion cannot be directly made for mechanical advantage unless the machine is assumed to be ideal. So we are able to conclude this only after the assumption, right? Otherwise, we cannot, come to this result. Okay. Now let's go to the next question, and here also we will get the guidance of how we can, if some number of pulleys are given and we have asked to design a block and tackle system, how to go about it. So a pulley system has a velocity ratio 3. Draw a diagram showing the point of application and direction of load, L, E, and tension. It lifts the load of 150 Newton by an effort of 60 Newton. So see here, we can calculate mechanical advantage because effort and load information is given to us. So we can calculate its mechanical advantage. And then they are asking, is the pulley system ideal? And if yes or not, whatever answer we say, we need to give reason for that. We need to justify that. So little guidance about coming question also, like if three pulleys has to be used, velocity ratio is given to 3, then how we can go about it. So first thing we have to think about, like velocity ratio 3 we need, how much pulleys we should have. This system will have how much pulleys, because that is not given directly. So we have to have equal number of pulleys as we need for the velocity ratio. So here we need to have 3. Okay, what to do afterwards? Just let's see the steps of guidance. First, decide how much pulley you need, then separate them in 2 blocks, or we can say sets, one fixed and one movable. One fixed will be at the top and movable will be in the lower one. Now, if the total number of pulleys is even, what we will do? We'll have same number of pulleys in each block. For example, if velocity ratio is asked as 4, so we'll have above 2 and below 2. And if it is an odd number, lower block will have one less than the upper block. So this is also like if in this example, the velocity ratio is 3. Now we can have in lower block also 2 and 1 in the above, but that will be a wrong thing to do because we want to have less pulleys in the lower block. So if we keep these thumb rules in our mind, then there will be no problem attending these kind of questions. Okay. If direction of effort not given, assume it downwards. Here, see, they have given the velocity ratio 3, but they did not mention which direction we need to apply force. So it is not, if it is not given, assume it, we have to pull it downwards. Okay. With above guidance points in mind, we can use as many pulleys as the velocity ratio. We can use that. Okay. And in the last step will be put tackle in the last step. Go block to block. Do not overlap tackles. Okay, let's go and attempt this question with this guidance. So VR is equal to 3. So we are concluding here. If we need 3, then block and tackle system will have 3 pulleys. 2 in a fixed block, right? And 1 in a movable. Why? Because it is an odd number. So the lower one will have 1 less. Okay. Now we have done like this. We are assuming the direction is like this, downwards, and then again we will go block by block. Let me put it here for the first one. So we will go block by block. We'll go down. This is the movable block. Then we'll go here, and then we will tie it here, right? Because there is no pulleys. Block by block we are going. This set we are calling the upper block, right? And this set is we called lower block or a movable block, because this upper block is fixed with the support. Okay, now can you see, put the directions also? A load will be downwards, effort will be this side downwards, but the tension due to this will be upwards. So here are the tensions. And can you count how many number of strands are here? Right? There are three. That's why velocity ratio 3 we are able to achieve from this arrangement. Now calculating mechanical advantage, it is given in the question how much load and effort we are pulling. We'll put those values that we are able to pull up the load of 150 Newton by 60 Newton of force. We will just take the ratio and we will get the value of 2.5. So see, it is less than 3. So this is VR is 3, but we are getting the mechanical advantage of 2.5. So it means mechanical advantage is lesser than the 3. Then we can comment like why it is happening, because it is not ideal. If it is ideal, mechanical advantage will come as exactly as VR, which is 3. As designed in ideal condition, only that will happen. But because there will be some friction, there can be sound dissipation of energy. Due to that, mechanical advantage in practical machines is always lesser than the velocity ratio. So this is the practical machine or practical pulley system they have asked us to design. Okay, so pulley system is not ideal. Why we got to know that? Because for ideal system, MA is equal to VR. Here 2.5 is of course not equal to 3. That is why we will say this pulley system is not ideal. Further, you can calculate the efficiency of the system. If they ask, just use the formula eta is equal to MA divided by VR. If they ask, we can calculate that this is 83% sufficient. Okay. Now let's go to the next question. So here is the eighth question here. Let's read this question. This shows a system of four pulleys. The upper two pulleys are fixed and the lower two are movable. Draw a string around the pulleys or put a tackle. Also show the point of application and direction in which the effort is applied. So this is important. Just putting the strings is not important. Only we have to put the directions also, but that's what they ask in the exams, like put the tackle and show what is the direction of load, where you are putting effort, where is the tension. So that is also important. So what is the velocity ratio of the system? How and load and effort are system, they are related means how much, like is they are getting multiplied by how much force we are able to pull the load. So that is what they are asking, what is the relation between load and effort, and we can calculate by calculating the mechanical advantage. D, what assumption do you make in arriving your answer in part C, this one, how you'll calculate this load and effort? So let's see, let's go one by one. First thing, we need to draw the tackle. So we'll start from here, go block by block outside, then we'll go another block like this, come here, right? And then we'll finish it off here. So this will be the diagram you will get in the end. So see how many strands are supporting the load? 4, right? So the tension, if it is T in this rope, it will be to 4T, and T will be equal to E. Whatever effort we will put, like if you take a rope and if you pull it with some force, how much tension it will get? It will get exactly equal to what effort you are applying. So don't forget it, that effort what we are applying is equal to tension. So we can get a relation between load and effort we are providing here. Okay, let's go. First thing, let's calculate the velocity ratio. The velocity ratio will be equal to the number of strands supporting the load, and that is 4. Okay, what is the relation between load and effort? So we have to assume again, because there is load and effort information in this question is not given. See, where is the load? Where is the information about it? Nothing is given. So we cannot just plainly say that mechanical advantage will be this. We have to assume that it is an ideal machine. If it is ideal, then we can say that whatever the VR we have calculated, the mechanical advantage is same as that. So mechanical advantage will be load divided by effort is equal to 4. And they ask like what assumption we have taken. We assumed the system to be ideal. So the effort is 1/4 of the load. We assumed the system to be ideal, right? Okay. Now let's go the next question. Question number 9. Let's read the question first. This figure shows a block and tackle system of pulleys. So this system is given to us, used to lift a load. How many strands of tackle are supporting the load? Draw arrows to represent tension in the each strand. What is the mechanical advantage of the system? How much effort is needed to lift a load of 100 Newton? What will be its velocity ratio if weight of the movable block is doubled? So that is also we need to calculate. Now see, here is the diagram. So I have put the arrow already. So this is the effort direction. This is the load direction. You can also put an arrow for the load direction, right? It should be from the load. Let me put it like this, right? This will be the direction of load. This is the direction of effort, and this will be the direction of tension, right? So can you count how many strands are supporting the load? 1, 2, 3, 4. So the velocity ratio will be equal to number of strands supporting the load, which will be equal to 4. Then they have asked, after marking it, how much effort is need to lift a load of 100 Newton. Okay, so let's try. There are 4 strands of tackle supporting the load. That's why the velocity ratio be 4 for this case. And if we assume again assumption that it is ideal, then mechanical advantage will be equal to velocity ratio. So from the strands, we can say VR is equal to 4, and that will be also equal to the mechanical advantage because other information is not given in this question. Now, as MA, we have to take load and effort, right? Will be only 1/4 of the effort required to lift up the load. So how am I telling that? See, the mechanical advantage is 4. It means we are able to generate 4 times the force. So if I need to pick 4 Newton load, I just need to apply 1 Newton because it will get multiplied. So if I need to pull up this much load, 100, then how much I have to give? Only 1/4 of that. So only 25 Newton if I'll apply, it will get multiplied by 4 mechanical advantage and I will get 100 Newton of force. That's why I'll be able to pull the load up. So this is the intuition. Otherwise, you can go with the formula also that M is equal to load by effort and M is equal to 4 and load is given 100. Then you can again MA will come this side, effort will go this side and you can solve like that also. Now, what will be its VR, velocity ratio, if weight of the movable block is doubled? So what they're saying, what if we increase the weight of this and make this movable block one pulley heavier? What will happen? So remember, the velocity ratio has nothing to do with forces. It is just by design, like on paper when we are designing something like this pulley system. So whatever we will think that this much velocity ratio should be there, that will end up being here. It will not change. What depends on load and effort is mechanical advantage. That is like when practically we will design, we'll make the machine physically, then we'll be talking about the forces, actual forces, how much advantage we are able to get, because in practically when we will build it, there'll be friction, right? The pulley we can make sounds, there'll be energy lost. So in that case, we will consider the effort and load. So even if you make it double or whatever, velocity ratio will remain same because that comes from, so if we are does not matter, does not depend on forces, then what it depends? It depends on the geometry of it, right? How much length it is, How many pulleys are there? What is the design? Like if you're drawing on paper, think like that. You can calculate right there what will be the VR of the system. Okay, so what will be its VR if the weight of movable block is doubled? It will be same. Okay, let's go next question. A block and tackle system has velocity ratio 3. Draw a label diagram of the system indicating the points of application and the direction of load and effort. A man can exert a pull of 200 kgf. What is the maximum load he can raise with this pulley of system if its efficiency is given as 60%? If the effort and moves a distance 60 centimeter, what distance does the load move? So let's first design a system. So because we need a velocity ratio of 3, I'll use 3 pulleys, right? An upper block, the fixed block, I will keep 2. So that is what the guidance we have learned from. So if odd numbers are there, we will keep 1 less in the movable block down here. And if you see, we'll go like, I can again do for you like this, block by block, right? Mapping like this. And then there is no pulley, so we will tie it here. So there will be 3 stands which are supporting the load, right? That's why the velocity ratio will come as 3. Now the question they're asking like how much load we can pick with this with 60% efficiency. What they're saying that VR is the ideal thing, right? We should be able to pick up 3 times, but the efficiency is lower. So how to approach this kind of question? Let's see. So eta is 60% or zero point 0.6. Our VR is 3. We can apply this formula, right? Eta is equal to mi by VR, or by intuition think about it. VR is 3. The efficiency is 60%. It means only zero point 0.6 of a 3 will be the mechanical advantage, right? If it is 100, it will be 3, exactly 3, because 100 means 1, efficiency as 1. So if it is zero point 0.6, it means VRs will be multiplied with some fraction, and that fraction will be 60%. That is what we mean intuitively by efficiency. So here you can use this formula, calculate MA, VR will go this side. So we'll get 0 0.6 into 3 and then 1.8. So this is the difference. VR is 3, but the mechanical advantage is lesser than VR, which is 1.8. Now, with this much advantage, this much force multiplication, how much you are able to, pull up the load. So that is why we will use this formula. MA is equal to load by effort. So effort is given to us. The person can only apply 200 kgf. We'll multiply it with our mechanical advantage, 1.8, and that will become our load, which will come as 360 kgf. So with this system, with this efficiency, we'll be only able to pull up this much of load. Now think about it. If it is ideal, how much it will be? How much load we'll be able to pick up? Can you guess? If this system is ideal, then how much load we will be able to pick? 3 times. If we are applying 2 kgf, we'll be able to pull up 600 3 times. That's what the VR will be equal to MA. So in that case, we will be able to pull up 600. But because the frequency is less, that's why we are able to pull up the lesser load. Okay, let's go next. Now let's calculate how much load will move if load moves 60 centimeters. So whenever we are talking about geometry, distances, we have to think about velocity ratio, not to the mechanical advantage. We'll go towards the mechanical advantage formula when we are talking about forces, efforts. Otherwise, when geometry case will come, distance covered in some time, arm lengths, we will always talk about the velocity ratio. So as the velocity ratio is 3, the load will move 1/3 of the effort movement, that is 60 by 3, 20 centimeter. So this is also intuitively we can do like this. Otherwise, you can do like with the VR formula, effort distance by load distance. Load distance we want to know. It will go here. VR will come here, and then we can do again. We'll reach to same conclusion. Very clear intuition about this here. See, if we are pulling it here, we are saying we are generating more force here, right? Because 3 stands are ideally it should be 3. 3 times force should be generated here. But when we are talking about the distance it will move, that will not matter upon the load how much we have put here. So if we are applying here less force and we are getting greater force, are we doing magic? No, we are trading off. So if this moves, x, our movable pulley moves x distance, we have to compensate that. We have to compensate that by moving this as 3x, 3 times, because the velocity ratio is like that. So we are not doing any magic. We are just applying lesser force, but the displacement is more. So that is what the main intuition here. Okay. Here is a question number 11. You are given 4 pulleys and 3 strings. 3 separated strings are given. Draw a neat and label diagram to use them as to obtain maximum mechanical advantage equal to 8. In your diagram, mark the direction of load, effort, and tension in each strand. How much has assumption have you made to obtain required mechanical advantage? And they have given us a very good hint. 3 movable pulleys will be there, 1 fixed pulley will be there, and with this into consideration, it will be very, very easy to make this diagram. So I have done one here. Let me show you my diagram. So 1 fixed pulley, and then there are 3 movable pulleys. So what we are doing, let's count the threads if I have used more than 3 or not. Let's see. So this will be my, let me change my color. So this is the effort direction downwards. So I'm putting 1 string here. Okay, and then going back and attaching to this. So this is my first string, right? I have used only 1 string, right? 1 string. So 1 fixed pulley and 1 movable pulley are connected through this string. Now with the connection of the second movable pulley, first movable pulley, we will attach the second movable pulley, and we will use the second string. So because there are 3 strings we can use, and we'll attach back to the fixed support. That's what the hint is also given. Right? 3 movable pulleys with 1 fixed pulley attached to the same support, same support. So they are common, the support is common to all the strings. So this is where my second string will be used, and then I will use the last one. Again, what I will do, movable pulley, I will connect it to the string, and the third pulley will be attached to that, right? And it will be connected to the same support going up. So that is how we are able to create the diagram here. And now we can put the tension where the tension will be there. So always like upwards like this, upward like this, the tension will be. So this they can ask, even they can give you the tackle, they already given the system, and they'll ask you to put arrows. So remember that why we are showing like that. So think about it, the load will be downwards, right? So the tension will be upwards. That's why they are compensating that. To pull this much weight, they have to be, these arrows should be upwards because they are supporting that. They are supporting that likewise, right? Okay. So we have, if you want to know the mechanical advantage, we need to get equal to 8. Then we have to assume that there are no friction losses, nothing, and the pulleys doesn't have any weight, because otherwise if these pulleys have weight and we are putting effort, think about it, we have to pull these pulleys also up. So that is why we are assuming here these movable pulleys does not have any weight, right? There is no friction, they are weightless, and strings are also inextensible. Is inextensible means they are not expanding. It should not be like, no, I'm if you're pulling it downward and it is getting stretched from here, not even applying force. So that should not also should happen. Strings also doesn't have any weight. So these are the assumptions we are making. Okay, let's go next question. Here we are designing a block and tackle system for construction site with following data set. Load is given and maximum effort is also given. And efficiency of system is given as 75%. Calculate a minimum VR required, the minimum number of pulleys required, and suggest a practical pulley system. Actually, we need to show that how we can use this pulley system. So first thing, what is the minimum VR required? So first we will calculate the because we are required. First we'll can calculate easily that how much is the mechanical advantage needed. So first thing we calculate load by effort. So we will get 7.5 or the efficiency is 75%. So that will be the 75% is the efficiency. Okay, and we can have use the expression of efficiency is equal to ma by vr. VR because we want to know. So we came through first mechanical advantage to calculate VR. Okay, so we are going indirectly. And then we can calculate that VR will be equal to 10. Solving this, we can get equal to 10. So here will be MA is 7.5 we have calculated because that information was given, load and effort. And then we divided by 0.75, that was efficiency. We are using this formula. And then we just need to solve for decimals here. This 100 will go up, 10 will come down, and 100 by 10 will be 10. Now suggesting number of pulleys, see what kind of velocity ratio we need. So our suggestion will come on the basis of velocity ratio. We will not take our suggestion from mechanical advantage. So whatever the velocity ratio is there, those many strands we need, that's how we will design the pulley. So suggesting number of pulleys, as we need velocity ratio of 10, we can achieve it by using minimum of 10 pulleys, 5 in the upper block and 5 in the lower block, because then 10 strands will be supporting the load, and we will get the exactly 10 strands and velocity ratio of 10. Okay, let's go next question. There are two students submit different pulley design. One is design A and B to lift a load of 2500 Newton with maximum effort 500 Newton and efficiency 80%. So what they are saying is the efficiency is common for both the designs. Okay, they are both used to use load of pull up load of this, and maximum effort they said we can apply only 500 Newton. Design A has VR of 5 and design B has a VR of 7. We need to calculate the effort of each design and justify which design is better. Okay, even without calculating effort, can't we say that if we have same efficiency, then if VR is 7, so this guy will win. The efficiency is 80% of this design also, design B and design A also. But here the VR is less, right? So because of this, whatever, because efficiency is same for both, we'll be having more mechanical advantage in this case, right? Okay, let's do it mathematically, prove it. So comparing mechanical advantage first in each case. So VR is equal to 5, here VR is equal to 7. Efficiency is same for both the design A and B. So we have to think like 80% as 0.8, here. Now again, we are using eta is equal to MA divided by VR, that formula. So MA mechanical advantage can be eta into VR. So 0.85, here 0.87. So see the mechanical advantage of design B is more, right? So if your mechanical advantage is more, lesser effort we need to apply, because we can now multiply with a bigger number. We can get more force generated as compared to this design. It will create only 4 times the force, and this will create 5.6 times the force. So of course the effort will be lesser here. But let's see. Now we can calculate how much effort is required by each design system to pull 2500 Newton of load. So mechanical advantage divided by, if we do the load divided by mechanical advantage, if we'll do, we'll get effort, because see so there is a formula, ma is equal to load by effort, right? And they are asking us to calculate effort. So what we will do, effort we will take this side, ma will come down, and we have calculated for both the systems. So here it will be divided by 4, here it will be divided by 5.6. So of course it will be 625 Newton, and here it will be 425 Newton. So can you say anything about which is design is better? Of course, this design better. We are able to pull up with a lesser force here. And also see, they in this the design first we are have to apply 625 Newton. But in the question, see they have clearly mentioned that lift a load of this one Newton with maximum effort we can apply is 500 Newton. So our the first design goes on toss, like we don't want to use that because it is taking more than how much we can apply the maximum effort, right? 625 is more than 500, but this is okay because we can apply this effort. So design B is better because you need to apply less effort, we can say like that. Okay, now let's go to the next question. To lift a heavy load of 600 Newton vertically, load is attached to a block and tackle system of 4 pulleys, 2 pulleys in each. The free end of rope is tied to a uniform lever of length 2 meter, pivoted at one end, at a distance of 0.5 meter from the fulcrum. A man applies effort E at the other end of the lever. Assume the system to be ideal. This language is little bit confusing. So what they actually mean is this we understood, like we have to use two above in the two in the above and two in the lower block, and load will be like this. So I have represented it like this. The free end will be attached where? So it will be attached. So this is the pivot. This is the pivot of the lever, and we have to attach this free end 0.5 meter from the end. So here it is attached. So this is a little bit confusing wording. That's why some people may tie it here. Then the answer will go wrong, right? They might think it will apply here and the fulcrum will be in between. No, it is not that case. They are the free end is joined here 0.5 meter from the fulcrum here, from here. Okay, so we have to apply effort like this. Okay, and now load will be, because we are pulling it like this, load will be here, applied here, and there is the R fulcrum. So can you tell me which kind of a lever this is? This is a second class lever, right? Load is in between anyway. So let's do now what we can do step by step what they have asked. Mechanical advantage, we have to calculate tension T. We need to calculate least value effort applied to lift the load. Is there an advantage of attaching lever? That we need to comment on. So let's first calculate tension for the load. Effort will be multiplied due to lever, right? That is there because see this arm length is more and this is less. So if we'll put an effort, it will get multiplied because there is a trade-off between distance and force. And we are assuming for an ideal system, right? If we have assuming it ideal, right, then we can say, so this has to be very clear that we are assuming it. MA will equal to VR. Then VR formula is this: effort arm divided by load arm. We are talking about lever here. So 2 meter will be the effort arm. So because this distance will be the effort arm from where it is pivoted to the effort, we are applying the effort. So that'll be 2 meters. And load arm will be 0.5 because we have attached this rope here. So this will be the load for the lever. So it will be 0.5. And we can see this will come as 4. So we have a mechanical advantage or a VR, velocity ratio, of 4. Now what will happen? We'll be able to, we will be able to, we'll be able to create 4 times the force by the lever itself. So is it helping us? Of course it is helping us, right? Before even applying here any taking any advantage of this pulley system, we already have made our force 4 times. So the lever is really helping. Okay. Now what will happen, since the other end is attached to the free end, T is equal to 4E, right? So we are applying E here, which will get the advantage is 4 times E. Now this V4E will become the tension here, right? These tensions will be all 4E, right? All 4E. This will be 4E, 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 like that. Let's do mathematically. Let's go further. Okay. So the tension will be same throughout the rope and that will be equal to 4E, that we can calculate. Now least amount of effort to be applied. Since 4 strands are supporting the load, we can say 4T is equal to load. right? See this diagram. From this diagram, you can see here the 4T. If I say this is T, okay. So 1, 2, 3, 4. 4T will be equal to the load which we are supporting. So 4T is equal to L, but we know T is equal to 4E because we have already, used lever. So tension is coming as 4 times our effort. And now we are, instead of T, we can put 4E, then it will become 16E is equal to L, E will be equal to L by 16. And now we can put what is the load we need to pick, 600. And when we divide it by 16, we will get 13.7.5 Newton as our answer. So pick up the load of 600 Newton, just see how much less force we need to apply.